So I'm going to talk about something that's kind of been my hobby for the last 8 years or so. When I first went to University of Chicago from Bell Labs, I was able to, there was no one there still is no one there who does computer graphics as a research area. So I was able to say, well, I want to teach computer graphics. And this wonderful thing about being professors, you can learn by teaching. And so I've been teaching a course every couple of years on computer graphics, and these courses are typically taught in traditional imperative programming languages. We use C for many years. We recently switched to using C++. But I wanted to be able to sort of play around with algorithms and things like that in a better language. And for me, that means standard ML. So I started hacking the standard ML OpenGL stuff, and that's what I'm going to talk about. Now, a year ago or so, maybe 2 years ago, I would have had a complete system to talk about because I had an OpenGL 2.1 system, which was very nice. But computer graphics has completely changed in recent years. And so this is sort of, it's a little bit of a work in progress because I've been re-implementing lots of stuff. And so that's what I'm going to talk about. Okay, so some background. If you look at the sort of standard flagship consumer graphics card from NVIDIA over the last 10 years, you'll see this. So this is based on a normalized benchmark. You'll see that there's been actually a huge increase in performance, about a factor of 60 in slightly under 10 years. Transistor counts have increased by more than 30 over that period of time. In fact, the highest point there is a GTX 7B, I believe, and it has almost twice as many transistors as the top of the line Intel Xeon Phi, or not Phi, but Intel Xeon i7. So the graphics hardware has really become this incredibly powerful thing, and as a result of that, I think we can actually really do interesting computer graphics in languages that aren't necessarily considered performant, although ML is not too bad. So what I want to talk about first is a little bit about because some of you probably have written graphics code, many of you probably haven't. And so if you go and look in the graphics book, the first thing they'll tell you about is the graphics pipeline. And this is what the modern graphics pipeline looks like. The colors quite reproduce as well on the screen as they do on mine. But so you've basically got two kinds of data coming from the user. You've got vertex data, which essentially is, you can think of these as points in 2D or 3D or 4D space. And you've got texture data, which is essentially 1D, 2D, 3D arrays of stuff like color. And there are two basic phases of graphics processing, so you can't really quite read it up there, but it says vertex processing in that larger sort of gray box up there. And then there's this purple box down here where it says fragment processing. And so the vertex data goes in and it gets transformed by the vertex processor, then it gets rasterized, and rasterization essentially is a process of turning something like a triangle into little individual points on the screen. There's some additional processing of the individual pixels, or what are typically called fragments. There's a final bunch of stuff that's done that's called blending, and out pops a T-pop. Yeah. So all this stuff in gray, the rasterization and blending, is stuff that is still done in hardware, in modern graphics cards. But all these blue boxes are actually programmable processors. In fact, they're basically the same processors, just passed to different kinds of programs. So the vertex shader, there are these pair of things called tessellation shaders, which are used to take a simple mesh and create a much more complicated mesh. The geometry shader, which does various transformations on individual triangles. And then the fragment shader, which does sort of per pixel computations. And so the thing is, we have all this horsepower sitting on the GPU, and all of that horsepower is programmable on the GPU. So, in fact, most of the interesting rendering problems are going to be written to run on the GPU. And so the language that we use on the CPU doesn't really have to be the most efficient, low-level language possible the way it used to be. Because if it's a good language for generating code, which many functional languages are, it's actually a good language for doing graphics. So, just to summarize, so we have this real rapid change in hardware, and then this previous slide here just sort of describes what the modern graphics pipeline looks like, which is evolved because of those hardware changes. So what this means is that the way we write applications is very different than it used to be. So on the CPU, we put together a big array of data, and we pass it as sort of using one or two function calls to the graphics library. We have these shader programs which we've downloaded into the graphics library. The graphics library compiles those basically at runtime, although you can sometimes pre-compile. And those shader programs determine how things get displayed on the screen. I guess I mentioned that. So, you know, the point I think I want to convince you of is that this programming model, where all of the heavy lifting, computational heavy lifting, is going on in what are essentially are runtime generated programs, or can be runtime generated programs, provides a lot of opportunities to do interesting things from the point of view of a functional language person. And just so one thing that we've done some work on in the past are looking at embedded domain-specific languages for graphics. And in particular, a few years ago, we had a paper at Paddle about such a thing for specifying particle effects. So these are basically using lots of very simple to draw and simple to simulate objects. You do a simple physics model, and the idea here was we developed essentially a combinator library which let you specify these effects. And since I think any graphics talk has to have at least some graphics in it, this is actually from that previous paper. But this is a demo. This is a movie captured from this thing. It's a little fountain. It consists of, I mean, there's some geometry there which is being drawn to make it look nice, but the interesting stuff is all these little white dots, and the white dots essentially are interacting with a physics model that includes some boundaries, some specifications of how things get generated. It's only 20 seconds, that's why I stopped. And various kinds of transitions, like when the water level fills up to a certain level, it goes. So this is all actually underneath the hood. It's all cheating, but if you throw enough particles at it, it can actually look plausibly realistic. So that's the kind of thing I think that we can do more easily in the context of functional languages, perhaps than in some other systems. There are lots of other opportunities. Image processing, so there's this work at MIT on this image processing language called Halide, which I'm sure many of you have heard of. There's Adobe has a thing called Pixel Blender, which is for building Photoshop plugins. Of course, functional reactive programming can be done in 3D. Why not? And then shading languages. So RenderMan, which is the classic shading language that companies like Pixar have been using for years, is a domain-specific, in many respects, a very declarative style, domain-specific language for writing these shaders that get used to render very complicated scenes. I won't say realistic, because obviously you're doing something like Toy Story. There's an obvious cartoonishness to it, but it gives you a lot of power and control. So that's just to give you some sense that there are actually some opportunities there for using graphics using functional programming to do graphics. And I'll talk a little bit about the library that I've been working on. Obviously, the Haskell has a very nice and mature library that people have been building, and I imagine OCaml probably has OpenGL support as well, although I'm not familiar with it, but this is what I've been doing for SML. So it's real-time graphics programming, so it's not ray tracing, it's not radiosity, it's not anything like that. It's actually trying to do things that will run in real time and interact with the user. It's built on top of the Milton SML compiler, primarily because of the foreign interface support in Milton. It's got a bunch of libraries, so the sort of lowest level library is something I call raw data, which basically implements a sort of a standard interface to the basic scalar types, which of course Milton supports already, but it just tweaks the interface a bit. A bunch of foreign interface utility code, things like being able to do malloc, that sort of thing. And probably most importantly, a memory buffer module that gives you a strongly typed buffers of basically tuples of various scalar types in the C heap, allocated in the C heap. And therefore, some of the OpenGL APIs, you actually have to use C allocated memory because garbage collectors tend to move things around, and that can cause problems. Then the main library is got linear algebra support. So lots of stuff like in the previous talk, except this is all very small scale, so 2D, 3D, 4D, matrices, vectors, quaternions, that sort of thing. The big piece is the core OpenGL API, and OpenGL comes in lots of different flavors, and depending on your operating system and your graphics card and other things, which version you have will vary. So what I'm trying to do here is provide essentially a sort of a layered implementation where you'll be able to compile against whatever version you choose, and that'll be a compile time option. But right now I'm mainly focusing on 3.2 for various reasons. And then there's a bunch of graphics utility code for things like representations of planes, triangles, rays, cameras, etc. OpenGL doesn't talk to the windowing system, so you need a library for that. I used to use the GL utility or GLUT library, but now I'm using GLFW. It's a somewhat lighter weight and more compatible with the modern OpenGL. You need to be able to read in and write out image data, so there's a library for doing that. Supports a number of standard image formats. And sometimes you want to do parallel computing in your graphics application, so there's some infrastructure for supporting OpenCL as well. So, in thinking about the design of this, there's this really big question, which is what is the right level of abstraction? And one approach is try to be as close and faithful to the C code as possible. Right? So this is in fact the Haskell OpenGL raw package does this. And if we were to take something like NLFFI and run it over the OpenGL APIs, it would give us a very C-like interface we're dealing with OpenGL. That gives you all of the mechanisms and all of the heartaches of programming in C. So it's not clear there would be much of an improvement. Another possibility would sort of go to the other end of the spectrum and build a high-level scene graph library. And if you go out and look at there are a bunch of these things you typically within C++ that have essentially let you describe a scene in terms of geometry, higher level geometry, things like meshes, things like various kinds of solids, etc. They have notions of cameras, they have notions of animation and whatnot, level of detail support, etc. And you build this model and then you hand it off, and the library is very clever about how it actually renders that and hopefully renders it in a very efficient way. And that's very nice, but you lose a lot of flexibility in those kinds of models. Plus, it's a tremendous amount of work to actually implement something like that. So I've what I'm trying to do essentially is give you access to all of the OpenGL API, or at least most of it, but doing it in a way that sort of fits with the style of ML, fits with the type security we hope to have. And I'll give you a couple little examples of that. So, first example, so OpenGL has some very vast number of symbolic constants. They're all of the same type. It's GL enum, which essentially is a 32-bit unsigned integer. But those constants are actually logically grouped in different types. And so the natural thing, of course, to do is to dump them into, I mean, one possibility would be to build data types out of them and to marshal and unmarshal back and forth. But for probably 99% of those constants, they're only really ever used, or they're almost always just used as arguments to functions. So just making them values actually works very well, and it also allows us then to use exactly the same representation as OpenGL uses, so we don't have any marshalling overhead there. It does mean that when you, in those few occasions where you actually want to test whether it's front, back, or both, you actually have to use equality rather than cases, and that's a little disappointing, but it's a reasonable cost. So we build interfaces like this one above. We define the equality type face. We define the constants. There are functions like call face, which take a face and do something. And underneath the hood, face is just one of these words. The constants are just defined to be the OpenGL constants, and the call face function is just a call to the underlying C function. A more interesting example comes from the texture code. So we use phantom types in ways similar to the previous talk, though perhaps not quite as sophisticated application of them. But one of the things here, this is a function for specifying the data for a 2D texture. And the function call, if you go and look at the manual page, there's a bunch of different things that have to be specified. In particular, you specify the internal format. So this is the format that's going to be used on the graphics card to represent the data. There's also the external format. That's the format of the data as you supply it to the function. And then there's the data itself, which is this image, 2D image here. And you really want it to be the case that those are all consistent in some way or other. And so we use phantom types to enforce that consistency. And here's some examples. So in the texture module, there's a value called iFormat RGB, which represents RGB triples, where the type variable here represents the type of the individual elements. There's a pixel module that lets you has special type constants, special value constants for constructing these instantiated phantom types. So like float.t of tie is the way we represent the floating point pixel or floating point channel representation, and then we have this function RGB, which would take one of those and give you back a format where you're going to have a float format. And RGB has a runtime representation, which is going to be the OpenGL symbolic constant that specifies RGB behavior. But in OpenGL, the C API, there's nothing to protect you from mixing those up and getting wrong, other than the library will do error checking on you, so your stuff just won't work. Anyway, there's lots of these kinds of examples, and I'm not going to give you more because it'll get boring. But I did want to talk a little bit about Milton. So the reason I'm using Milton is primarily because of the foreign interface infrastructure. You get direct calls to C. And it has, particularly, it has very nice data interoperability. So base types like int, bool, string, etc., can be passed directly to C functions without any explicit marshalling or unmarshalling. Furthermore, if tau, so if we call that being able to pass it to C as being C compatible, if tau is C compatible, then so are tau vector, immutable vectors of taus, tau arrays, so mutable ones, and tau references, which essentially you can think of as arrays of length 1. So we can do things like have an array of strings and pass that to OpenGL, and that's great because the way you represent a shader program is as an array of strings. And so you can build up your shader program in your ML code and then just ship it off that way without having to convert it into a C data structure. It also gives you access to C pointers and C arithmetic, etc. So this is all stuff that's done inside the implementation. It's not stuff that end users use, but it's very helpful to have this to actually make these things work. And the other thing you need when you're dealing with user interfaces, like mice, keyboard, whatever, is to be able to support callbacks. And in fact, Milton does allow you to define ML functions that can then be called by C. So the foreign interface stuff is actually, in subsets, is probably the hardest part of building the system. OpenGL is huge. It's got, as of yesterday, it has 695 functions. It has almost 5,000 symbolic constants. It gets updated frequently. That's why I say as of yesterday. If I went and did an SVN get today, it might very well, there might be a new extension or something like that. And every year, lately at least every year, there's been a new version of OpenGL. The most recent came out around the beginning of August. That was 4.5. Fortunately, there are machine-readable specifications of the API, and that makes life a lot easier. So we built a tool system, the tool for taking these specification files, and these specification files used to be written in this horrible, undocumented, line-oriented syntax, which various people had. There were a bunch of Perl scripts or something that they supplied for processing them. Various people, including the Haskell people, and myself, had reverse engineered the format to then try to bring it into something more reasonable. But fortunately, they eventually got around to actually replacing it with XML. So it's now all XML. It's much easier to deal with. So I'll just quickly explain what's going on here. So I have this program called GLDB, which basically takes those specifications plus this box called extra, which I'll explain in a moment, and it produces this GL core file. And that's essentially has all of the information about the APIs reorganized in various ways. I have a couple of tools that consume that. GLGen, which generates most of the OpenGL stuff. It generates the constants. It generates a whole bunch of different function files, basically different function files for different versions, or at least at the sort of 2.0, 3.0, whatever. And there's also this thing, there's some of these groups, like the face group that I showed you before, that are actually documented in the XML file. Unfortunately, not all of them, but some of them are. And so this group gen basically uses that information to synthesize those kinds of definitions. And then there's this targets JSON file, which is just the way to drive all of those tools. So it's essentially the make file for generating the specifications. So see what that kind of looks like. So this is my XML format, not theirs, but it's fairly similar. And this is the specification of the draw elements function. And it has a return type, it has some parameters, they have some various types. You can see here there's this group annotation, which is essentially a sort of saying, well, really, this is an enum, but it's really part of the primitive type group. So that's a place where you get a little bit of extra type information. But if you take that and you generate something out of it, we end up with this Milton import here, where you're given it a type of enum cross size cross enum cross pointer. Pointer is a C pointer. And that turns out not to be very useful, because we would like to be able to call this function with, say, an ML array or an ML vector. We might want to call it with a vector of 16-bit integers or something like that. And all we have really essentially is void stuff. And there's no way to go from ML data structures to C pointers. So that's where extra comes in. It lets us specify additional types for functions. So we essentially import things at multiple types. So in this case, it has this horrible name, draw elements vec UV, but what that ends up being is we annotate that, the indices argument with an explicit ML type. We say, yeah, it's void star on the C side, but really it's a word8.word vector. And when we generate the ML code, we'll get two different functions, both bound to the same C function. So two different ML functions, one of which happens to have this word8 vector type. And that's basically that extra mechanism lets me deal with a lot of the typing issues in how we access the API. So that's worked out fairly nicely. So I'm probably almost out of time. So quick status thing. So I hope to be able to say it was complete, but it's taking longer than expected. That's the story of my life. But it is really almost complete, and there are the other parts are complete. So raw data, GLFW, Manjaro. There's actually even documentation, which is again, like the GLFW is completely documented, but some of the other parts are not. This you should ignore that because that wasn't supposed to be on the slide. That's fine. So future work. So one thing is this question about using phantom types to force constraints is, I mean, you know, in some sense it represents, it's sort of as good as it gets in the ML language, right? If we had, well, in OCaml you have more mechanisms, in Haskell you obviously have lots more mechanisms, et cetera. But in standard ML, which is sort of classic Henry Milner, this is about as good as it gets in terms of enforcing these kinds of runtime invariant constraints using the type system. And I think it's actually expressive enough to do a lot, but it's not clear to me where the benefits of having a stronger typing outweigh the cost of having really very complicated kind of type encodings. And that's something that I've been experimenting with and playing with. And I'm not sure exactly where, you know, there's obviously one in the spectrum is you just let the user write code that can have runtime type problems. I've tried to avoid that, but where exactly I want to draw that line, I'm not completely sure. And in particular, dealing with vertex attributes, which essentially are the per vertex data that gets fed into the vertex shader, is one place where there's a lot of choice there. Textures have a tremendous amount because there are all these different formats, and then there are things like compressed formats and various other horribleness. It gets very, very complicated, and again, it's not clear where you want to draw the line. The bindless style. This is who's actually written an OpenGL program? Is anyone? Okay, so you know there's this horribleness that you have where you have to go, you know, bind whatever, bind the texture, bind the buffer, bind the vertex array object, and then modify it, right? And all the code, all the functions that modify things do so with respect to whatever the most recently bound object of that particular kind is. And that's horrible. And NVIDIA has, for quite a few years, has been arguing, no, this bindless model, and they've had an extension available for quite a long time, but not available on all platforms, that supported sort of direct access. So instead of saying bind the texture, set its clamping mode, you just say set the clamping mode of that texture to whatever. So it's sort of more, you could say, object-oriented. In 4.5, this is now part of the core API. And I have to say, I'm sort of tempted to back. I mean, you can implement that thing if you do caching and keep track of what the current texture is, what the current whatever is. And so I'm sort of tempted to just bite the bullet and actually implement that API, even though it's not exactly true to what's going on under the hood. It's a lot more convenient. And my hope is that the performance cost wouldn't be too great. So that's something that I'm thinking about. We need lots more utility libraries, particularly by going to GLFW. Glute actually had texture rendering support, although it really was for the old version of OpenGL, not the modern version of OpenGL. But text rendering is something really neat. Just want to give thanks to Pavel and Sam, who were, as undergraduates, have worked on this project. Pavel did a lot of the work on the particle system stuff. Matthew Fluitt has been extremely helpful in terms of explaining how things work in Milton and fixing bugs and fulfilling feature requests, etc. And Matt Rice, who I've never met, but has sent me bugs, so that's good. So I'm happy to answer any questions.
So I'm wondering if you make any effort, and if so, how successful you are at, when you call a C function, when you're passing it like one of these word out arrays, can you catch whether the C is going to run off the end of that and crash the whole process?
Oh, actually, so that, most of the time, that you can avoid because you actually, because in ML, you know the lengths of things, and in this buffer library I have implemented, I keep track of that kind of information as well. So for those kinds of functions, you always specify the length when you call them. I mean, it's part of the API typically. But I mean, if you go back to that draw elements, there was the size. That's the length of the array, elements array. But I don't. For the user, you just say, "Give me the array," or "Give me." You don't use that API. You use a slightly cleaner API where the length. So that kind of stuff is fairly straightforward. The place where that's trickier is, so draw elements actually is an array of indices into other arrays. And so without it, this is, I don't know, for people who saw Tim Sweeney's PLDR, keynote many years ago, one of the things he was arguing for in terms of having a dependent type system was exactly for that scenario, because that comes up all the time in graphics. That kind of extra indirection is essentially one of the key techniques they use to increase performance.
Does the OpenGL runtime system take ownership of these strings that you pass them, or?
It copies them, yes. So in fact, so that's not 100% true, and then this is the place where the buffer stuff actually becomes, so it's history. So it used to be the case that there was client-side data, and that's actually the reason I originally created the raw data stuff. It was client-side data, their ownership issues were a little bit more complicated. Then, when they went to this new programmable-only interface, everything became server-side, library-side, whatever. And so everything was getting copied. But then, of course, they said, well, now we have these new GPUs that have, shared address space with the CPU and all that stuff, and we want to exploit that. So there's now APIs that allow you essentially to have, for both the CPU and the GPU, to be accessing the same memory, and then there's sort of an explicit protocol you have to manage to tell the GPU that things have changed and whatnot. And so in that case, you really need to allocate stuff in the C heap.
So I've mainly used OpenGL through Jacques Gourit's LabelGL library with Camel, and he went a bit crazy with polymorphic variants, mainly because I think he's wrote them. It's been one of the most useful parts of the library because one of the hard bits of OpenGL is all the extensibility of all the new extension mechanisms and so on. And so the use of polymorphic variants, both in values but also in phantom types in functions, has been a key part of the extensibility of that use of the library. So do you have any thoughts on how you'd make your library more future-proof?
No, actually that's a very good question, and the short answer is this case, in fact, earlier this week I was thinking about exactly this case because I was working on the shaders code, right? So I'm OpenGL 3.2 shaders, you have just three kinds: vertex, fragment, geometry. 4.5, 4.4 shaders, you have tessellation shaders of two flavors plus compute shaders, which I didn't mention, but are essentially like OpenCL. So I had this issue about exactly that because I used phantom types. And so in the end, in that case, what I did is I just put that information into the interface of, but it's not, it's sort of, in a way, it's not supported. But there's no way to create those values, but there is a way to write those types down, essentially. And that's one thing one can do, but obviously with the extension, I mean, the extensions are really a nightmare to deal with in this, I mean, for lots of reasons. I mean, I think one of the biggest problems is the whole business about runtime configuration, because that's really, if you look at, industrial strength OpenGL programs, they dynamically test, because it doesn't depend on what header file you have, it depends on what driver stack you're running on. And you might actually have a machine with multiple driver stacks that implement multiple versions of the API. And so, it's messy and it's horrible, and we don't, in some sense, we've sort of pretended that those kinds of terrible things don't happen. And so, we haven't really designed our languages to accommodate that kind of awfulness. And it's a flaw. I mean, it's something that we probably ought to be thinking about harder, but you're not going to get it. I don't think you'll get a PhD.
I sort of following on, do you know how they actually deal with that problem in terms of writing the code like against this kind of, where you don't know which API you're running up against? So that, and then the other question is, like, do you want like type providers for OpenGL? Like,
well, I mean,
dynamically create types off of discovering what you had as a program?
I don't think you need the dynamic thing, because you really algorithmically you need to know what the features are and what they do. So when you write the code, you have some idea. Oh, there's this extension which if I use that extension, I can make my critical path run faster. But essentially, what they do is they do specialization, where they have typically up front. They do some querying of what are the capabilities of the underlying device driver, and then so does it support extension X? And if it does, then they're going to go down code paths in which X is used, and they use dynamic loading linking often to. You have two situations. So one time, in some situations, you're actually guaranteed the API points even if they don't actually do anything. So you effectively get runtime errors, and in some other situations you essentially just use dynamic linking. And if you're on Windows, Microsoft stopped officially supporting OpenGL after version 1.1, so everything beyond 1.1 is dynamically linked, because the OpenGL library, the Microsoft libraries that you compile against don't actually support that stuff.
Just one thing, I think you might be able to get a PhD out of it, because one thing I played with Metacandle back in the day to introduce software rendering fallbacks whenever the hardware things weren't available. So Metacandle way back then was bytecode only, but now it's got ASIC support as well. So I'm sure you can build the next Quake in Metacandle.
I kind of maybe you have a program generation, right? So what you kind of said is, and also it's typical for systems like single assignment C, where they generate several variants of code, depending on some of them dispatch to, depending on what the runtime information available. So the precompiled is that dynamic contribution.
Yeah, I mean, I think one of the biggest things now is that so much of the computational load is on the GPU, and there's issues about which version of the shader language you have and things like that, which every time they up the version number of OpenGL, they change the shader language as well. So it's really actually kind of a nightmare in terms of porting. But because of that, a lot of these differences can essentially be masked in which shaders you use, and there are a lot of people have various preprocessor infrastructure to specialize shaders for a particular target.
More questions?